Gauss law by Prakasham, ECE. Basic concept: electric flux, Gauss law, application of Gauss law, conductor in equilibrium. Electric flux: the electric flux pi E through a surface is defined as the scalar product of E and A. A is a perpendicular to the surface with a magnitude equal to the surface area. This is true for a uniform electric field. What about the case when the electric field is not uniform and the surface is not flat? Then we divide the surface into small elements and add the flux through each. Here is the formula. Here is the example of electric flux. Compute the electric flux through a cylinder with an axis parallel to the electric field direction. The flux through the curved surface is 0 since E is perpendicular to dA there. For the ends, the surfaces are perpendicular to E and E, A are parallel. Thus the flux through the left end is minus EA while the flux through the right end is plus EA. Hence the net flux through cylinder is 0. Gauss law. Gauss law relates the electric flux through a closed surface with a charge Q inside that surface. This is a useful tool for simply determining the electric field, but only for certain situations where the charge distribution is either rather simple or possesses a high degree of symmetry. Problem solving strategies for Gauss law. Select a Gaussian surface with symmetry that matches the charge distribution. Draw the Gaussian surface so that the electric field is either constant or zero at all the points on the Gaussian surface. Use symmetry to determine the direction of E on the Gaussian surface. Evaluate the surface integral. Determine the charge inside the Gaussian surface. Solve for E. Conductors in electrostatic equilibrium. The electric field is zero everywhere inside the conductor. Why is this so? If there was a field in the conductor, the charges would accelerate under the action of the field. The charges in the conductor move, creating an internal electric field that cancels the applied field on the inside of the conductor. Here is an example. We can also use Gauss law to determine the electric field just outside the surface of a charged conductor. Assume the surface change density is tau. Since the field inside the conductor is zero, there is no flux through the face of the cylinder inside the conductor. If E had a component along the surface of the conductor, then the free charges would move under the action of the field, creating surface currents. The C is perpendicular to the conductor surface, and the flux through the cylindrical surface must be zero. Consequently, the net flux through the cylinder is EA, and Gauss law gives. And here is the formula.